Eratosthenes pictured a section of the earth whose outside edge ran from Alexandria to Syene, a city in southern Egypt. If he could figure out the distance between Alexandria and Syene, and if he could measure the inside angle of the section they created, he would be able to calculate the earth's circumference. But how would he ever be able to measure that angle? It lay far below the ground at the center of the earth. Eratosthenes realized that the sun could help him with his angle problem, and he picked Syene for a reason. He had heard from a caravan passing through Alexandria that on the 21st day of June, at precisely midday, the sun would shine directly down a certain well in Syene, lighting up the well, but casting no shadows on its walls. But at the exact same time in Alexandria, shadows would be cast. Eratosthenes knew why. It was because the earth was round. If the earth were flat, the sun would strike every place at the same angle, and the shadows would all be exactly the same. Eratosthenes knew a thing or two about shadows and angles. He knew you could measure the angle of the sun by the shadow it cast, and he knew from the mathematical texts he had read that the angle of the sun in Alexandria at noon on June 21st would be the same as the angle that lay at the center of the earth, making the inside of his Alexandria to Syene grapefruit section. So Eratosthenes walked out of the library a few minutes before noon on the 21st day of June to measure a midday shadow at Alexandria, just as the sun was falling straight down the well at Syene. He measured an angle of about 7.2 degrees. Then he divided 360 by 7.2, which equals 50. Now he knew that it would take 50 Alexandria to Syene sections to make up the circumference of the earth. But knowing that was still not enough. Eratosthenes had to know the length of his section's arc, the distance between the two cities. Then he could multiply this distance by 50 to find the distance around the whole earth. It would be so simple. But it wasn't. There was a problem. The problem was camels. Camels were the main manner of transportation in the desert, and Eratosthenes had planned to measure the distance between the two cities by calculating how long it took camels to get from one city to another. He thought camels would be perfect, but he forgot that they are ornery, stubborn, and have minds of their own. Some camel caravans went slow and some went fast, and some camels ran off in the wrong direction. No matter how hard Eratosthenes tried, he could not record travel times for camels that were accurate enough for his mathematical equations. Finally, he threw up his hands in despair. Enough with these camels. I'm going to see the king. He asked the king if he could borrow the services of his best beamatists, surveyors trained to walk with equal steps. In this way, linear distances could be measured with some accuracy. The king agreed, and the beamatists he supplied walked with equal steps just as they had been trained to do. It was then easy to estimate that the distance between Alexandria and Syene was 5,000 stades. A stade was supposed to equal the length of a Greek stadium. The stade that Eratosthenes used was 515 feet, or just under 1/10 of a mile. Eratosthenes now had all the numbers he needed for the formula. He calculated the circumference of the earth to be 252,000 stades, or 24,662 miles. When the earth was remeasured in this century, there was only a 200-mile difference between the modern-day figure and the one that Eratosthenes had calculated over 2,000 years ago. Eratosthenes' measurements provided the first accurate mathematical-based map of the world. His Geographica, the first geography book of the world, was now complete. Eratosthenes lived to be a very old man. He continued to work on math problems and to study and measure the earth. But most important of all, he kept asking questions. No question was ever too big or small for Eratosthenes to think about.